Hello, my name's Alan Smith. I'm a developer, trainer, mentor, evangelist for a company called Active Solution based in Stockholm in Sweden. The session I'm going to be delivering is talking about game services and telemetry processing in Microsoft Azure. When we typically think of cloud computing and the typical load patterns that we work with cloud computing applications, we're often introduced to these types of patterns. We have these kind of one-off or one-off events, which are kind of things like the Olympic Games, where we get a lot of demand on a particular site or service over a short period of time. We've also got things like Twitter, which during, as it was building up and getting more popular, they had a rapid growth pattern. I'm a big Formula One fan. The Formula One racing site has a very predictable load on it. We get very high intensive usage patterns at the weekends when they're running a Grand Prix, but at the other times there's a lot less activity on the site. And it's very predictable because they know that when the Formula One calendar is, when these actual bursts of activity are going to be on the site. Things like news sites like bbc.co.uk, we have this unpredictable burst where we can have a major news event happening in the world, and that's going to produce a rapid demand on the site very, very quickly. And it's completely unpredictable. This could happen with 2 or 3 minutes warning any time. When working with game development, we have another usage pattern, which I've heard to as being referred to as launch week. When a new game is launched, there's very intense activity on the back-end services that are powering that game, and that activity may run for a couple of days or a couple of weeks, depending on how popular the initial release of the game is. But after that initial release, there's going to be less and less activity on those services. So it's really a service that we're deploying that's going to be downscaling over time. But it's critical that these services are running effectively once the game is released. Halo on the Xbox is an example of a game that uses Microsoft Azure technologies. They use the usual services that we've got in Xbox Live, such as membership leaderboards, achievements and downloadable content. But then within Microsoft Azure, they're providing additional game services for games presence, things like cheating and banning and multiplayer game stats. And to augment this, we've got a Halo Waypoint application that can run on Microsoft tablet devices, so players can actually interact with the game in different ways. And these services are provided using some of the core services in the Microsoft Azure platform. There's a great webcast on Channel 9 where Clemens Vastas and Hoop Samoa are talking about some of the implementations of those technologies. So if you want more information, that's definitely worth checking out. As I mentioned, I'm a Formula One fan, and one of the things that's becoming very key in the Formula One industry is the use of technology in motor racing. There's a sponsorship partnership between Microsoft and the Lotus team to be able to assist the team to be able to work with telemetry data, processing all of this data and helping the team to analyse how their cars are performing on the track, and hopefully leads to better lap times and better positioning in races. Within each Formula One car, they have a standardised engine control unit, which is the same across all of the cars that are competing in the races. Telemetry data is also very important for the drivers and the teams, so they need very complex systems to be able to get the telemetry data from the engine control units and be able to process that telemetry data to be able to improve the performance of the car and so on. This also leads into an industry that there's a lot of talk about now with the Internet of Things. People are talking about connected devices and being able to have things like fridges, air conditioning units, motor vehicles, soda dispensers, all kinds of advertising and display systems, weather stations connected up to the Internet. And there's two technologies that are making this, enabling this at this present moment in time. One of these technologies is the advent of cloud computing and cloud-based services. We've now got the resources to be able to develop and deploy systems that can scale rapidly and store vast amounts of data that the telemetry from these systems is going to be generating. We've also got a big prevalence of Wi-Fi networks. So it's very easy for devices such as a car to be able to connect through a wireless network and to be able to send data to the cloud. Also for systems that are installed around business premises to be able to hook onto the business's Wi-Fi network and interact with cloud-based services. We have at the company where I work these competence development projects, and one of the development projects that I'm involved with is looking at the Internet of Things. So what we see here is a small computer called a Raspberry Pi. We've got an additional board plugged on that Raspberry Pi, which is called a Pi brick, and that allows the Raspberry Pi to integrate with Lego Mindstorm sensors and motors. And because the Raspberry Pi is a programmable computer, we can interface the Raspberry Pi with services that we've got running in Azure and be able to actually read the telemetry data from the sensors and send control messages out to the motors. This is a coffee machine at work. It's again an internet-enabled device. The coffee machines are placed on weighing scales which are hooked up to another Raspberry Pi. We can see that in a bit more detail there. And that's sending condition monitoring data from the actual coffee machines out to a website. So within our organisation, this is in Swedish, but what it basically says is that we do have coffee in the coffee machines. There's 10 cups in machine 1, 7 cups in machine 2, and we can see a picture coming from the Raspberry Pi of anybody who's going to take coffee. So this, although it's a fun project, it's something that can help us to understand how the Internet of Things is going to work. This same technology could be used for monitoring thousands of coffee machines in lots of companies and sending back telemetry data, condition monitoring data on how well those coffee machines are performing. So you could send out an engineer to target a specific coffee machine that's going to be need to be serviced, rather than sending out engineers to all of the coffee machines on a weekly or monthly basis. Another example of telemetry data, this is again from Clemens Vastas on Channel 9, is looking at how we can use a Raspberry Pi to send real telemetry data from a car. And this is a great webcast. Clemens starts a webcast driving down the Autobahn in his Audi, and he's sampling the telemetry data from his car using a Raspberry Pi, sending that through the 3G network in his car. And that information is going to table storage, and we can analyse that data and look at the actual performance of the car, the engine temperature. So these technologies that were initially pioneered in the Formula One industry are really sort of filtering down to other industries in the Internet of Things technologies. When we're working with the Internet of Things, there's several architectural patterns that we can use for exchanging data between the services and the actual devices themselves. One of them that I'm going to be talking about a lot during this session is telemetry. Telemetry basically means remote metering. It's a way of being able to take information sampled on a regular basis and send that information off to a back-end service. So it can be a stream of data sampled once every second, or 10 times a second, or once every minute, and so on. This is also sometimes referred to as condition monitoring when we're talking about industrial automation. If you've got a wind farm, you want to be sending data on how that wind farm is performing at a regular basis. And that's the same thing, telemetry or condition monitoring. Another pattern that we've got is inquiries. So if you've got an air conditioning or a heating system at home, that heating system could make a request out to a weather service and get an actual prediction on what the temperature is going to be in the evening in that particular area. And that's going to help the heating system to run more efficiently. There's no point in heating up the apartment if it's going to be a warm evening. There's no point in turning on the air conditioning if it's going to be cool in the evening. So sending out inquiries, gathering that information, can help the systems to run more efficiently. Commands are very useful. Supposing I'm going out for a meal with friends instead of going home, I can actually use a mobile device to tell my heating system not to turn on until 10 o'clock at night instead of 6 o'clock. And that again can give me more control over the actual systems and be able to help save energy. Notifications is another example. If you've got a navigation system in a car, it would like to receive notifications if there's any accidents or traffic queues, and be able to actually help to route the cars differently. So this is the actual services themselves sending out information or messages down to the actual devices. So the project that I'm going to be talking on, it's a pet project that I've been working on for a while, and I've given it the name of Red Dog Racing. We've got Red Bull Racing, the Formula One team, and we've got Red Dog, which was one of the original code names for the Windows Azure technologies. So I've basically chosen that as being the name for my game. The code that I've written is basically been modifications to an already existing sample. So I didn't write the game myself, but I have done some heavy modifications in the game to integrate it with Azure and provide some tweaking in the general game mechanics. So the sample that I started with is called XNA Racer. It's available for download on the XNA platform if you do want to experiment and look at the kinds of scenarios that I've been working with. So I love working with Microsoft Azure. I love looking at the technologies that we've got available and seeing how these technologies are emerging and how organizations can use these technologies when they're developing systems. I like physics. I was good at physics at school. I kind of had a natural ability to be able to understand these types of questions, dealing with Newton's laws of motion and dealing with basically the mechanics aspect of physics. So anything that's related to speed, velocity, acceleration, that's stuff that I like working with. I'm a Formula One fan, so anything that's kind of related to motor racing and especially how the technology in that industry works is going to be useful. And also, I like playing driving games. Play quite a lot of games on the Xbox, and being able to go in and see how a game works and understand how that game works. It's good fun to be able to actually look at those types of technologies. So the idea behind the Red Dog Racing project is to look at how Microsoft Azure can provide an integration and be able to provide services that can help to actually make this game more of a multiplayer game, and to be able to score things like high scores in table storage and display that information on the website. It's also relates a lot to the Internet of Things, because instead of using a computer game, it could be a real car, it could be a device, it could be anything that's sending telemetry data to Azure. So I'll run through a quick demo of how the actual game works. So I've got the solution in Visual Studio here. So I'm going to start this solution in the debug mode. Now we should see two applications appearing here. One of them is the driver tracker. Now the driver tracker is basically subscribing to the Azure service bus, and it's looking at the actual live data that's coming from people who are playing the game. Now when we're doing the Azure Conf, we've got several speakers here. You can see Martin and Noopman, who are basically also going to be doing sessions here. They're in another room currently playing this game, and what we're seeing on the driver tracker is these actual drivers, their actual real-time positions on the track. We can also see Andy Cross has just started a lap there. We've got a website for the game, so we can go into the game's website and we can see the actual scores here. So here's the overall standings. If we go to the beginner track that they're driving, you can see that Martin's got the highest score here. We've got Cheerio behind that, Noopman and Andy Cross down here. So these are basically the actual lap times, and this is going to be updated as the players are actually competing at laps in the game. The other application that started here is the actual game itself. So what I'm going to do is to position the driver tracker and the actual game itself next to each other. So when I actually start running my lap, you can see my gamer name there is Alan. You should see my actual position appearing on the track, and I'm going to try and compete with these guys and beat their times. I've got an advantage. I'm actually using an Xbox controller for Windows, so it gives me a bit more control of the car. So I'm going to go in to play the game. I'm going to choose the Azure car. I'm going to choose the beginner track and see if I can actually drive a lap and compete with these guys. So what we'll see as I'm driving, we'll see actual ghost cars appearing on the track, and these are actually from blob storage. It's not the actual real-time positions of the cars, but it's the actual using the actual lap data from the fastest laps that these drivers have been set. So every time I overtake a ghost car, I move up one position in the actual scoring. You can see that I'm currently in 6th position. But hopefully, if I drive smoothly, I should be able to gain a couple of positions going around the rest of the track. So I'm currently in 5th. I've gained another position, overtaken a ghost car, and hopefully I should be able to overtake another couple of cars before the end of the lap. So I've still got 5th place. There's probably about 15-20 seconds left of driving here. I don't think I'm going to catch the guys in front, but hopefully I should be able to get a fairly respectable time. And you can see my actual position appearing in real time on the driver tracker. So there we go. I got in 5th place with a time of 104.22 seconds. And if I exit from the application, refresh the website, you should be able to see that that time is now appearing on the actual list of times. And I can go into the actual lap and I can view the actual telemetry data that's coming from that particular lap. So you can see my speed, you can see when I was crashing, you can see the damage on the car. Down here, we can actually see the driver input. So we've got the throttle appearing here, we've got the brakes, we've got the current gear that I was driving in here, and we've got the actual steering appearing here. And this is all done using Azure technologies and using Azure services. So I'm going to talk through the solution and think about how we're actually going to be creating the solutions and how we can use Azure services to be able to build these types of scenarios for games and for the Internet of Things. The Microsoft Azure platform provides a great range of services that we can use for building both cloud-based and hybrid applications. And one of the challenges I find when designing and architecting Azure solutions is, we've got this great range of services available. What services should I choose when I'm going to be building my application? To add to that challenge, the services are evolving rapidly. So new capabilities are coming into various services. There's a lot of new release cycles coming through. And it's great to see this technology evolving at a rapid pace. But sometimes it can be challenging for developers to understand how best to use these services. So I'm going to talk through the solution and talk about the services that I'm actually using to implement the Red Dog Racing scenario. So what I did, as well as looking at the services that I've got available, I went back to the information exchange patterns that we've talked about with the Internet of Things and said, well, it'd be really nice to take these architectural patterns and see how we can implement them to make the driving game work. The first one is telemetry. This is really important in Formula One racing, also condition monitoring, and also in the games. You want to actually see if somebody's driving faster than you. You really want to understand why they're driving faster than you. When are they accelerating? When are they braking? What steering input are they putting? What lines are they taking around certain corners? And so on. So the game is actually sending telemetry data. It's sending timing data first, which is the driver details, the sector times and the lap times, and that's used to provide the actual scoring on the website. And then for the graphs, it's sending very detailed telemetry data from the game. We're sending the car position, the driver input, and lots of parameters from the actual physics engine are going out into table storage. And I'll talk about the architecture and how I built this solution as we go through the session. Inquiries. When the game starts, the game is going to display the best lap times for the drivers. It's also going to download and make requests for the actual data to be able to display the replay data for the ghost cars that are driving around the track. So this is the example of the game making a request out to a REST-based service to return the information about the lap times so it can display them. That's the example of an inquiry pattern. Commands. I actually use this racing game in a workshop where people are going to learn to work with Windows Azure, and they actually have access to the source code. So if you're a creative programmer, the first thing you're going to do when you get access to the source code for a driving game is increase the power of the engine, reduce the weight of the car, and make the actual car drive faster than it should do. I kind of thought that was cheating, so what I put in the game is a way of being able to monitor the telemetry data that's coming in from the game, and then make decisions and decide if a driver has cheated or played around with the physics engine. So what I do is I basically monitor the things like the car speed, the car acceleration, and if, for example, the car is driving at 400 miles an hour, basically the race control, this logic would know that something's wrong in the physics engine, and it would punish the driver. And the way I do that is I send a command out to the game that converts the 400 miles an hour of forwards velocity into 400 miles an hour of vertical upwards velocity, which is a good way of being able to prevent people from modifying and fooling around with the physics engine. Helps to keep a level playing field. We've also got notifications. For the notifications pattern, I'm using the services hosted in Azure to be able to send notification messages to the players who are playing the game. So when another player completes a lap time, I can send a message using the service bus, which will appear on the actual players of the game. So they can see who they're competing with and get updates when new lap times are set. Also, the race control system will send out information when drivers are under investigation and also when other drivers have been punished. We've got these text-based notifications coming up on the screen. So now let's take a look at the architecture that I'm using to build this application in Microsoft Azure. I'm using several Azure technologies. For the messaging capabilities, I'm using the Azure Service Bus. I'm using topics and subscriptions to actually get the telemetry data into the worker roles that's going to be processing that telemetry data, and also out to the driver tracker that's showing the live driver tracking information. I'm also using the relay service in the service bus to actually send out the in-game messaging to be able to broadcast messages to the other players in the game. I have in Azure Services, I've got an Azure worker role. The worker role is responsible for dequeuing the telemetry messages in the service bus, processing that information and inserting it into storage. So we've got a storage system storing that data. Within Azure Storage, I'm using a couple of the services there. I'm using table storage to store the driver lap times and the driver telemetry data. And then I'm using blob storage, a blob container with blobs in it, to store the actual binary driver replay data. And that's going to be used to generate the ghost cars. In order to host the website and the services that I'm using for the game, I'm using Azure Websites, which is a basic, I've got a basic MVC application with a couple of Web API services to actually supply the data to the game and also to the graphs which are drawn in JavaScript. So when the game starts up, the game is going to be sending telemetry data into the service bus, which is going to be processed by the worker role and stored in storage. When more people start playing the game, if we get multiple players, we get a lot of load building up on the system. We've got the option of scaling the worker role tier to be able to actually handle that additional load. Currently, with the amount of players, I've been fine running on one worker role, but if there's hundreds or thousands of players, we need to increase the capacity and be able to scale. And it's very easy to scale the worker role tier to be able to handle that processing. Then we've got the website, and I built a very basic website just to display the information for the lap times and so on. Now, when I was creating this architecture, I thought, it's okay for this Red Dog Racing game, but it doesn't meet, that many customer scenarios maybe. So I really wanted to think about the architecture that we would build for an Internet of Things scenario. And it's not going to be that much different. I mean, we've got various devices that we've got running that are generating, things like telemetry data, conditioning, monitoring data. We need to send commands and notifications out to these devices. So we have technologies like the Azure Service Bus. These devices can be programmed to communicate with the queues and topics and subscriptions in the service bus and be able to actually send information out to those systems. We've got the worker roles, and in this case, they're just going to be processing the telemetry data that's coming from these various devices. We'll use the same architecture for storage and maybe even use a website so people can go in and interact with these various devices. So this type of architecture that I've created is going to be very versatile when working with an Internet of Things project. So let's have a look at in a bit more depth about the actual implementation of the scenario. The first thing we'll look at is the lap time and the actual scoring that we're using to send the information out to the actual website. So what I'm using is the game to actually send information through the service bus, and that information is ending up in table storage. Table storage is a great way of being able to store large amounts of data using a non-relational format. So what we can do is look into the actual storage account I'm using for the actual lap times, and we can see the actual way the lap times are being scored. So I've got these various tables here. There's 3 tracks in the game. So this NDC player lap times 0, player lap times 1, player lap times 2. This is used for actual scoring the times for the particular laps. So if we go into this game here, this table here, and select the data, what we can see is that the partition key here is the driver name. So when it says Alan, that's the laps that I have set. You can see the actual row key here, which is a timestamp when that lap was set. And then we can see the information that I'm storing here. So I'm storing the type of car that was used, the amount of damage that was sustained to the car during that lap. We've got a unique lap identifier, which is used to basically identify this lap in the storage services. We've got the start time. We've got the lap time in milliseconds. So for the completed laps, this is basically showing how many milliseconds it took to complete that lap. And then we've got the level. We've got again the actual player name, and here we've got the actual sector times, which shows me at particular points going round the track, what my time in milliseconds was at that particular sector. And if we scroll down the table, we'll basically see that we've got different people who've been playing the game. You can see different driver names appearing here. Now, when working with table storage, one of the things that we want to do is to be able to store vast amounts of data. And we also want to make it very efficient to query that data. So when I'm querying on table storage, one of the most efficient things that I can do is to select all of the entities in that table that are in a given partition. So the best way to query this table is to say, give me all of the entities where the partition key is equal to Alan, or equal to Martin, or equal to Andy Cross. And that's going to return all of the actual lap times for me. So going into the actual website, what we can see when we go back to the overall standings, I can actually click on my driver name here. And this is basically showing me all of the lap times that I've set on the beginner's track. So I've got, it's coming basically starting with the earliest lap here and the latest lap here. And it's basically showing me all of my sector times, all of my lap times. And this is good for drivers to be able to go in and say, okay, well, how have I been performing in that particular lap? So that data is selected from that table. And we've got a table for each lap on the game. Here you can see the player lap times at 1 for the middle track, and this is for the expert track here. Player lap times 2. So another way of partitioning the data that you can do in table storage is to generate multiple tables. So I've got one table for each particular lap, and then I'm using a partition key in that table for the actual driver here, and that's used on the website to give me the actual driver times here for each particular lap that I can select. For the high scores, we really want to be able to have the same information, but we want to be able to query that data differently. So if we go into the rankings lap times table, I've taken a different approach to how I set the partition keys and the row keys on this table here. You can see that the partition key is set to the track name. So I've got track 0 appearing here. If we scroll down, you can see that I've got track 1 and then track 2 appearing here. And then I've got pretty much the same data, but it's stored slightly in a slightly different order. I've got the player name appearing here. You can see that Martin has set a lot of the fastest times on that particular lap. We can see the lap start time, we can see the level, the car type, the damage, and we can see all of the sector times running across here. So this is basically built to be queried in a different way, and when we go onto the website and query for the overall standings and query on the beginner track, you can see here that I'm not interested in all of the players for the specific lap. I'm interested in querying for a specific number of laps, but having the fastest lap time appearing at the top. So using partition key is great for being able to actually specify what data we're selecting. But ordering that data, it's great to be able to use the row key to be able to actually define the order of that data. So what we can see here, if I expand the table a bit, is that the lap time in milliseconds that we're setting here for this lap, that's 59423. And if we go to the actual row key for this entity, you can see that I'm using 000599423 here. Now, within a partition, the data will be ordered according to the row key. So being able to use the lap time 0 padded for the row key means that if we beat that lap time, if we do a lap in 58 seconds, that's going to be 00058 whatever, and that's going to appear at the actual top above that entity. So the row key, combinations of the partition key and the row key allow us to be able to query the data very efficiently and get the lap times in the correct order. I am doing some filtering, so I basically query the entities from the table, and if we get duplicate player names, I will actually remove those. So the second player should be Cheerio, third player should be Newtman, or Know What Man. If we go back here, you can see we've got these 1, 2, 3 appearing with the actual lap time. So another thing that we notice when we look in this table is the way that I'm storing the sector times. You can see that for track 0, if we pan along and look at the sector times, we run up to sector 7 and sector 8. If we scroll down the table and get on to track 1 and track 2, you can see that we've got additional sector times. Because the second track is longer and the third track is even longer, we've got 13 sectors on the second track. And on the longest track, we've got 23 sectors. Now, one of the things when I'm talking about table storage, I don't talk about rows and columns. We talk about entities and properties. And I'm actually using dynamic table entities to actually store this data. And it means basically that these aren't table columns. It means that these entities here, they don't have a null value for this. It's just that that property doesn't exist for that entity. So table storage is very versatile for being able to store these dynamic entities that may have different properties associated with them. And that's why I've basically chosen in the code to use dynamic table entities for the lap times, because the laps will have different sectors when I'm storing that data. And it's very easy to code and build solutions using those systems. So if we go and look at how the telemetry data is stored. For telemetry processing, I'm going to be sending the data a lot more frequently. We're basically sending information up to Azure once each sector is completed in the game. So a sector is completed roughly every 10 seconds, and a lap is completed on the fastest lap in about 1 minute. So sending out the telemetry information, we really want to have a fine-grained or high frequency for sampling this data. So we're actually sampling the data 10 times a second during the racing game. The racing game can run at maybe 50, 60 frames a second, and I basically take samples of the telemetry data 10 times a second. Now, we have to think about scalability here. If I was sending the data or sending messages to the service bus, 10 messages a second from each player, that's really going to slow things down with a lot of players. So what I do is I actually send batches of telemetry data every second up to the actual service bus, and that's basically how I've built that solution. If you look at how Clemens has built the solution using telemetry in his car, he's doing something very similar. I think he samples the data every second, and he sends a message every 60 seconds up to the service bus containing the last minute of driving, and that just helps us to decrease the load. You will notice when I was running the driver tracker that the positions were moving around in sort of 1 second jerks, and that's because of this 1 second interval where I'm sending out that telemetry data. So the game is basically sampling up this data and then sending a message onto the service bus every second. So let's look at how this is implemented in the Azure solution. So if we go into the Azure portal, what we can see in the service bus section is I've got a service bus namespace called Red Dog. And if you go into the Red Dog namespace, there's a couple of topics here. One is for the player messages, and one here is for the actual telemetry. If you look in the telemetry topic, we can see a bit of the load that we're placing on this. And this is, you can see here at this point, we had 692 messages running on it. And we've got various other statistics coming through. And this helps us to analyze, how much load we're placing on these various services. If we go into the subscriptions, the way that I'm using the topics and the subscriptions is when a message is sent to a topic, that message is broadcast to all of the subscriptions on that topic. So currently, we've just got one subscription, and that is the Telemetry Worker. Now, Telemetry Worker is a worker role that I've got running in Azure. So if we go into the Cloud Services, into the Red Dog Worker, we can see that in the instances section here, I've just got one instance of a worker role running. For high availability, you really should have at least 2 instances running here, but we're just using this as a demo here. And going to the actual configuration here, we can see, to the actual monitoring here, we can see the actual load that we're placing on this worker role. So what this is showing is the actual CPU percentage that we've been using during this session. So we peaked at 2.97% at CPU. So I'm putting very low utilization on this. But scalability is very easy when we're working with Azure technologies. I can go into the scale option here. I can decide that I want to scale this worker role up to 2 instances and click on Save. So if I detected that more people were playing the game, I can just scale up the instances like that. I can also build in auto-scaling capabilities. So if the CPU goes above a certain level, we could make it automatically scale up and increase the number of instances. So after a few minutes, that should generate another additional instance on that. So if we go back to the service bus and I go into the Red Dog namespace and into the actual telemetry topic and look at the subscriptions, I'm basically using a publish subscribe pattern here. I'm basically got the game, and the game is sending messages to that topic, and we've just got that one subscription that's going to the worker role. We'll see another subscription appearing here as we get another instance of the worker role being created. What we can also do is add additional subscriptions or dynamic subscriptions. So when I start the application, the driver tracker is also going to want to subscribe to telemetry messages. It's not going to store those telemetry messages, but it's going to use those telemetry messages to display the information about the drivers on the track. I'll just exit from the game from now. So going back to Azure into the portal, what we can see here is an additional subscription has been generated using a GUID. So this means now that when anybody is playing the game, they will send a message out to the actual telemetry topic, and that message will be delivered both to the actual worker role that's doing the processing and also to the actual driver tracker. And if we start additional instances of the driver tracker, I'll start a couple of instances of this. You can see that we've got additional subscriptions being created here on that particular topic. And that allows the telemetry data that's being sent from the game to be broadcast off to multiple systems there. So it's very easy to build a secondary or a third system that's going to be processing that telemetry data. So as well as using the telemetry data for the driver tracker, we're also storing that data in storage. So let's take a look at the telemetry data and how that's stored in table storage. So looking at the ranking laps table, we can see that we've got a lap ID, and that lap ID is used in the telemetry table as the actual partition key here. We also need to think about how the data is sorted. So the telemetry data is basically coming out in the order of time. So what I'm using as the row key here is the time in milliseconds that we are around the lap. So this telemetry data is going to come out in the same order in which it was generated. So again, I'm using multiple tables to partition the data, using the partition key for how the data is going to be queried, and using the row key to determine how that data is going to be sorted. So within the actual physics engine, we're tracking a lot of things. We're not showing all of those things in the actual graph, but here you can see I'm tracking the acceleration. We've got the driver inputs such as the brakes percent, the throttle percent and so on. We've got the car type, the damage, and then we've got the actual 3D coordinates here, the X, Y and Z direction. Things like distance above ground if we're doing a jump. Also additional things from the physics engine. So when I was playing around with the physics engine, I was working with things like downforce, drag, engine force, force velocity, all this type of stuff here, you know, what gear we're in, and various other options here. So this is providing a lot of detailed data that we can actually query and analyze. And we'll talk about telemetry analysis a bit later in the session. So I'm using the worker role, as I mentioned, to dequeue the messages, put that data into table storage. The website is then running queries on this data. And you can see it's appearing in the form of a graph. Now I'm actually using a graphing API, a JavaScript graphing API. So we've got services that are hosted in the website where I can actually query that service and it will return in a JSON format the actual data that can be then used to actually display it in the graph. Telemetry storage and analysis. Using table storage allows us to store a lot of data. We can literally store billions and billions of entities in a single table in table storage. It's a very cost-effective way of being able to store that data, and there's a very good performance on that, provided we're making intelligent use of the partition key and row keys to actually query that data. So as well as being able to actually display the information in the graph, we can also do telemetry analysis. And this is where things get really interesting when we talk about scenarios working with the Internet of Things. Being able to have vast amounts of data and then be able to query and analyze that data effectively. So what I've done here is built a very simple application that's going to be doing a bit of telemetry analysis. I'm querying into the laps table, getting a number of lap IDs, and then querying into the telemetry table and getting all of the actual telemetry data. Now what we're seeing on the screen here, it's not an actual picture of the lap, it's basically the positions of the cars that have driven around the lap, and that's basically giving me lines around the lap. You can see in some places just about here, there is a bit of variation in where the actual cars are. It's a bit hard to see, but I have actually added some colouring. So the lines are red when the car is travelling slow, green when it's travelling fast. So this gives us an indication. You can see this was the start where the car started at 0 speed, they then accelerated. We've also got this corner here, a bit hard to see, but the lines are slightly red around here because the cars were going a bit slower around this particular corner. I also track in the telemetry data when any damage was caused to the car, and I'm highlighting this with the actual red dots. So here you can see that people have been crashing. Around this particular corner here, it's actually a blind corner in the racing game. You can see that there were quite a lot of crashes at that particular point there. So by analysing this telemetry data, I'm only using it with 10 or 20 laps here. By analysing hundreds or thousands of laps, we can basically see where drivers are crashing. We can see what's the best speed to go into a corner. We can see the actual optimal lines that the fastest drivers are taking it around the track. And pushing this out into other industries, if you're a taxi service, for example, or a delivery service, being able to see where your taxis are, being able to see how long it takes to get to point A to point B at a specific time using a specific route and be able to analyse that data. It's going to be very powerful for those industries and technologies to be able to use and analyse this data. The replay data and the ghost cars, I'm using blob storage to be able to store this data. So what I'm doing is basically making a slight modification to the original game to achieve this. So when you download the original game, the XNA Racer game, the XNA Racer does have ghost car functionality. So for the fastest lap, it will actually store the data for the ghost car in binary format on the actual hard drive of your laptop. And that means you can race against your own best time, and you can basically play against yourself and race yourself. However, what I really wanted to do was to introduce a multiplayer element and a bit of competition to this game. So I made a slight modification to the code of the game. So instead of saving the ghost car to the actual local storage on the machine, I'm actually uploading the data for the ghost car in binary format into a blob storage. And you can see in the actual storage account here, we've got a blob container called replays. I'll jump into this in the actual storage explorer here. So if I close the tables, go into the blob containers here, we can see that we've got a replays container here. And I'm basically using the name of the blob with the actual track that we're using, and then we've got the lap ID, and then we've got .replay. So this is kind of a proprietary format that the game is using to store this data there. So here are the blobs. For the advanced track, we can see the actual size. It's about 38 KB. For the beginner track, we're running at about anywhere between 18 and sort of 25 KB. Really depends on how long it took to complete the actual lap. And this binary format contains a lot of the sample data, the car's position, the car's direction. And it's this data that's used to actually display those ghost cars when we're actually racing around the lap. Blob storage, like table storage, allows us for massive scalability. So I could literally store millions and millions of these actual ghost car data in the actual game itself. So you could, if you wanted to extend on the functionality, build one where you could choose a particular player. You could choose myself, or you could choose Martin, and you could race against Martin's best laps and see how Martin is actually driving around the lap. And the cost and the scalability of this, allows us to make lots of actual storage and be able to utilise those scenarios. So one thing about telemetry, people use telemetry in different ways. One thing that's really important for motor racing is live telemetry. And this is when, like I'm using the service bus, I'm sending that live data. Because if the car engine is overheating, or the tyre pressure is decreasing, or there's a problem with the car, the pit crew need to know about that immediately. So real-time telemetry data, that can be sent as an actual data stream using a messaging system. And we've also got this option of using batch telemetry. So sending the batch telemetry, this is kind of like I'm doing it with the actual storage. I'm waiting till the car's completed a lap, and I'm sending an entire batch of information for that lap, which is being stored in a binary format in a blob storage. Now, it is a bit of redundancy here, because I'm pretty much storing the same information in these blobs as I'm storing in the table storage and the telemetry tables. I could optimize this and say only use the actual telemetry tables and use the actual data from table storage to drive the actual ghost cars. However, I wanted to keep both of these scenarios in the actual implementation, just to show examples of how these two scenarios work. In-game messaging. This is a way of being able to, make the playability work in a game in a multiplayer scenario. What this allows us to do is to be able to send messages out to the actual game from the system that we've got processing in Azure. So the way that this works is that we've got our telemetry data going into the actual service bus, and I'm actually using the relay eventing service in the service bus to actually broadcast these messages. So what happens with the relay eventing service is we expose an endpoint in the service bus, and that endpoint is then used by all of the actual players in the game. So you can see that each of the actual game screens there has its own endpoint present on it. Now, the way that the relay service works is the endpoint is actually located, it has a URL which is in Azure, which is in the actual Azure Service Bus namespace. However, there is basically a relaying operation taking place. So when a call is made to that URL that we've got in the cloud service, the actual messages are routed out to the actual instances of the game. So it's a bit like saying that the services are hosted on-premise. They're actually hosted in the game itself, but the actual endpoint for the service is hosted in the cloud. And we've got the relaying technology actually sending those messages down to those actual services there. So what this allows us to do is to have the games being able to expose their own endpoints, which are reachable from outside on the internet. The people who are playing the game are currently sitting on a wireless network within a Microsoft building, and they don't have an external IP address, but we can still reach those services using the actual relay service. It allows us a way of being able to relay the messages there. So what happens here is we're sending our lap data and our telemetry data into the service bus. That data is being processed by the service bus, and it's being stored in table storage. But what we're also doing is we're actually monitoring that data and processing the actual telemetry data in the worker roles. Now, when somebody sets a lap time or sets the fastest lap or has a crash or breaks the rules or whatever, we may want to send out a notification to the other players. So what the worker roles can then do is make a call out to this endpoint that's hosted in the relay service. And when that call is made, it's broadcast to all of the people who are playing the game. And that will basically result in a message appearing on the actual screen and scrolling up the screen saying Alan has set a lap time of 1 minute 34.10 seconds. So again, this is a nice way of being able to demonstrate how we can use these Azure services to be able to sort of improve the playability of a multiplayer game. So just a note on using the relay event service. This doesn't really scale to a massive number of players. So with a few people playing this or running a racing game workshop with 10 or 15 players, this is going to be fine. If you really want to go to a multiplayer service, there's better technology. So you could use the event hub, you could use topics and subscriptions to be able to broadcast those messages if you did want to have additional scalability on that. So, thanks for listening. I hope you found this presentation useful. Takeaways from this. Firstly, when you're building a solution in Azure, take a look at all the services that you've got available to work with and decide which is the best service that you're going to use. Are you going to use queuing in storage or queuing in service bus? Analyze these services and see how they fit. Also, the patterns and practices that I've been talking about during this session, I'm using them in a fun scenario, which is a driving game. However, I feel that these technologies and this architecture can be really useful if you're working on Internet of Things, connected devices, anything like that. Thanks very much for listening. My name is Alan Smith.